Hello OT learners, and welcome to today's video where we'll be talking about indirect or inverse variation. This is the online tutor, and coming right up is the introduction to indirect or inverse variation. As discussed in our previous variation tutorial, we said that variation shows the relationship between two or more quantities. In today's video, we want to look at the indirect or the inverse variation and how to write the inverse variation mathematically. We said that two or more quantities vary indirectly when one quantity increases and the other decreases. For instance, assuming we have quantity A, and then we have another quantity B. If these two quantities are inversely variated or vary inversely, if they vary inversely, what it means is that if quantity A increases, quantity B has to decrease. If quantity A decreases in size, then quantity B has to increase in size because of the variation being an inverse variation between them. So which means the relationship between quantity A and quantity B is an inverse relationship. So the progress of one means the what? The regression of another, and the same way the regression of another means the progress of another quantity. Let's have a look at an example. So if we have y varies indirectly as x raised to the power n, this relationship can be written in a mathematical form. So mathematically, we write y varies indirectly as x raised to the power n as y. This is our variation sign, and then to show an inverse relationship, we write 1 over the second quantity, which is what? X raised to the power n. So this statement is a statement to show that y varies inversely as x raised to the power n. Now, we need to remove the variation sign or the proportionality sign when we want to solve this particular equation. So to remove the proportionality sign or the variation sign, we introduce a constant. Now, like I said in the previous tutorial, when we remove the proportionality sign and we introduce a constant, the constant can be any variable at all, so long as it doesn't collide with the two quantities given in the question. So, for the purpose of our tutorial, I will be using k as my constant, but you can define your k as any other variable and use it in solving your question. So to further simplify this expression, we write y is equal to k. The k is now our variation constant or our proportionality constant. Then we write the expression 1 over what? X raised to the power n. Note that the k over here, which is the constant, is multiplying the equation 1 on x raised to the power n, which implies that we can rewrite this over here as y is equal to k on x raised to the power n. And this now becomes the expression to show that y varies indirectly as x raised to the power n, where y and x raised to the power n are our quantities, and then our k is our variation or proportionality proportionality constant. Let's have a look at a simple example to see how we apply this to solve a question. So assuming we have, let me say example 1. Assuming we have y varies inversely as x, and y is equal to 14 when x is equal to 3. We are to find x when y is equal to 30. So let's try and work out the solution for this problem. So solution. We've been told in the question that y varies inversely as s. So let's write down that expression first before we proceed. So we have y varies inversely as what? X. So it becomes y, then the variation sign, then we have 1 over x, which is the next or the second quantity. To remove the variation sign, we introduce a constant. So this becomes y is equal to k multiplied by 1 over x. So this expression can be simplified as what? Y is equal to k on x. Now we've been told that when y is 14, x is 3. So with these two values given to us, when we do the substitution into this equation, assuming this is equation 1, we will be able to find our constant or our variation constant. So let's go ahead and do that. If we do the substitution, y is equal to 14 and s is equal to 3, we have 14 is equal to k on x, which is now 3. This implies that if we cross multiply over here to get the value of our k will now be equal to 14 multiplied by 3, which will give us a value of 42 when we compute this into our calculator. So 14 multiplied by 3 will give us what? 42. This means that the relationship between our y and x, which is the inverse relationship, ideally is supposed to be written mathematically as y is equal to 42 on s. So this becomes our variation equation. Now note that the variation equation here is the same as the variation equation here. The only difference is that here we've been able to compute the value of the constant when we were given two variables, that is y to be 14 and then x to be 3. Now let's now find the value of x when y is equal to 30. So when y is equal to 30, we have, let me create some space. So let's continue. Now, when y is equal to 30, we do not know our x, but we know that the equation or the variation equation is y is equal to 42 on x. This means let's do the substitution. Wherever we find y, let's substitute the value 30. So we have 30 is equal to 42 on x. To find the value of x, this has a denominator of y, so we cross multiply. So we have 30 multiplied by x will give us 30x to be equal to 1 multiplied by 42 will give us 42. So our value of x is now 42 on 30, which will give us the result of 42 on 30 will give us 1.4 as our answer. Now let's note something. Let me use a different color to denote that. we can see that in the first instance, when y was 14, x was 3. So which means y was big over here, and then x was what? Small over here. Okay, we realize that when y in the second scenario has increased, okay, the y in the second scenario has increased from 14 to 30, we realize that the x value that we have has decreased from 3 to 1.4. So the x value has decreased. It has decreased from 3 to 1.4. This proves that the relationship between x and y is an inverse relationship, and the fact that as one value increases, the corresponding x value has to decrease because the relationship is an inverse relationship. Now let's have a look at an actual question to be able to solve for us to further enhance our understanding of inverse variation. So let's look at example number 1. The time required to travel a given distance, is inversely proportional to the speed of travel. If a trip can be made in 3.6 hours at a speed of 70 kilometers per hour, how long will it take to make the same trip at 90 kilometers per hour? This is a typical physics question involving what? The speed of a vehicle and then the distance traveled. So let's go ahead and look at the solution for this problem. So solution. We have here the time required to travel a given distance is inversely proportional to the speed of travel. So it means our first quantity over here is time, and then it is being compared to the second quantity, which is speed. Now, because we've not been given any variable to denote the time and then speed, we can choose our own variable to denote time and speed. So I will say let t be my time, and then let s be my speed. You can choose any variable that you want, so long as you define your variable, you are good to go. So we've been told that the time required to travel the distance varies inversely as the speed of travel. So it means our time t varies inversely as the speed of the vehicle. So to remove the proportionality sign, like I said, we introduce a constant. In our case, our constant is what? K, now multiplied by 1 over s. So it is safe to write that t, which is time, is equal to k on s. As at this point in time, I believe we all know how come we have this. So let's proceed. We've been told that if a trip can be made in 3.6 hours, let me use another color for that. So if a trip can be made in 3.6 hours at the speed of what? 70 kilometers per hour, how long will it take to make the same trip at what? 90 kilometers per hour. So let's look at that. In the first instance, we have the time to be 3.6 hours, and then we have our speed to be 70 kilometers per hour. So let's go ahead and calculate the value of our constant of proportionality. So to do that, we substitute the value of the time and then the speed into the equation we have over here, assuming this is equation 1. So we have 3.6 to be equal to our constant on the value 70, which is our speed. So to get our constant, we simply cross multiply. Our constant now becomes 3.6 multiplied by 70. So if we compute 3.6 by 70, we get 252 as our result, or the value for k. This means that the actual equation showing the relationship between the time traveled and then the speed is equal to time equals 252 on the speed. So this becomes our actual variation equation, assuming the question asks you to find the variation equation. So this becomes our variation equation. Now, the second aspect of the question is telling us to find how long it will take to make the same trip but at a different speed. So we have what? A higher speed. Okay, so our new speed is 90 kilometers per hour, and we are to find the time it will take for this. Now, straight ahead, there is a conclusion that I can make from this question. I know that my initial speed was 70 and it has increased to 90. And the fact that the relationship between the time and then the speed is an inverse relationship, I am confident enough to say that I'm expecting a time which is less than 3.6 hours as my time travels in this case. So let's go ahead and see if that is actually true. We know that our variation equation tells us the time is now equal to 252 on s. So it implies our time is equal to 252 on our speed over here is 90 kilometers. So we have 90 kilometers per hour. If we compute this into our calculator, 252 on 90 will give us 2.8. Then we add hours to it. So it means for the same trip, if the speed of the car or the vehicle is increased to 90 kilometers per hour, it will take a lesser time, which is 2.8 hours, for us to reach the same destination. So this now proves that what as the statement I made earlier on, that I'm expecting my time to be lesser than the initial time given, is actually true, and the fact that the speed has increased from 70 to 90 means the time has to reduce, and that is what we've seen over here, that the time has reduced from 3.6 hours to 2.8 hours. Now let's have a look at something. For those of us who are physics students, there is an expression that is really important for us when we are doing dimensional analysis. Okay, so we are going to go through that. But if you're not a physics student, don't worry, this expression is also going to be helpful to you as well, so long as you are doing variation. So we have the frequency of a string. So the frequency, which I'm going to denote by f, of a string is inversely proportional to the square root of its mass per unit length. Okay, so the frequency is inversely proportional to the square root of the mass per unit length of a spring. Mathematically, if I say let my frequency be f, okay, let frequency be f, and then let my mass per unit length, okay, so mass per unit length be equal to m, it means this expression I have over here can be written as frequency varies inversely as the square root of the mass per unit length, which is m. So assuming we have two different strings, okay, so for two different strings, we are saying string A will have the frequency fa to be what? Proportional to 1 over the square root of the mass per unit length of A, or alpha. Okay, And then for the second string, we have frequency of B to be proportional to 1 over the square root of the mass per unit length of B. So from here, I can further simplify this to be, let me simplify this first. My f of A will now be equal to k, which is the constant, on the root of what? The mass per unit length of A. And the f of B, the frequency of B, will be equal to k, which is our variation constant, on the root of what? Mass per unit length of B. But since k is a proportionality constant, okay, since the k we have over here is a proportionality constant, it doesn't matter whether it's for spring A or spring B, our proportionality constant, which is what? K, or our variation constant, variation stroke proportionality constant is the same, which implies that if this is Ka and Kb, then we are saying that Ka is equal to what? Kb. This implies that if we make Ka the subject over here, we are going to have the expression Ka to be equal to f of A multiplied by the square root of Ma. The same way we have Kb to be equal to f of B multiplied by the square root of M of B. This way, if these two are actually equal, it means that from this expression, we can have f of A multiplied by the root of Ma will be equal to f of B multiplied by the root of what? M of B. If you want to express these two guys in a ratio form, okay, where we have f of A and then f of B at one side, we divide. If we divide this side by what? F of A, we need to divide this side by what? M of B. In that way, we are going to have, if we maintain the f of A over here, we are going to have f of A on f of B will now be equal to what? The square root of what? M of B on the square root of what? M of A. So this becomes the expression to show the relationship between two strings having frequency and their mass per unit length. So let's note this expression as we are going to use it in solving a problem for the next question. So let's look at the next question that we have. So example number 2. Two strings of the same length and under the same tension gives nodes or frequencies in the ratio 4:1. Find the corresponding ratio of the masses of the strings. We get to realize that over here we've not been given any values for the frequency and the mass per unit length, but we've been given a ratio. In this way, it is hard to compute two frequencies to get a proportionality constant. So in this example, we need to use the expression that we've been able to derive in the previous scenario that I showed for us to be able to solve this question. So we are going to use the expression we have over here, this expression, to solve the problem in the next question. So let's go ahead and look at that. So we've been told that frequency A, the ratio of frequency A to frequency B is what? 4:1. Okay, if that is the case, we've been able to establish in the first case that frequency A to the ratio of frequency A to frequency B will be equal to the square root of the mass per unit length of frequency B and then string B, to the mass per unit length of string A. this was the expression that we derived. Okay, so straight ahead we can go and solve this problem. So we have 4 over 1 as the ratio we've been given over here, that is the ratio of f of a to f of b, to be equal to the square root of mb over what? Ma, the square root of ma. So to solve this, we need to get rid of the square root sign we have over here. So we square both sides. If we do that, we get rid of the root signs over here, and then we have m of b on m of a to be equal to 4 squared will give us 16, and then 1 squared will give us 1. Okay, so which means the ratio of, if we interchange the position over here to have our a at the top, ma on what? mb will be equal to, we need to interchange this side as well, will be what? 1 is to what? 16. This implies that the ratio of what? ma to what? mb will be equal to what? 1 is to 16. This implies that the corresponding ratio of the masses of the string, that is the mass of string A and then the mass of string B, the ratio is what? 1 is to 16. So this brings us to the end of today's tutorial. Thank you so much for watching the inverse tutorial. If this is your first example that you're watching or your first tutorial, kindly go and check our playlist on variation to see the example or the tutorial on direct variation before you proceed to the indirect variation. In the next tutorial, we are going to be talking about joint variation, which will be a combination of direct and indirect variation. My name is Samuel Kotuka, known on YouTube as the Online Tutor, and you can follow me on Instagram at the Online Tutor 990, and also do me a favor by subscribing to my channel, the Online Tutor, to make my channel grow bigger. Thank you once again, and I will see you in the next variation tutorial. Until then, keep safe and bye bye.